Good evening, ladies and gentlemen, and welcome to Highlands Astronomical Society November monthly meeting. We're gradually getting all our sound systems refined, but we had a few glitches tonight, but we're getting there, And in the last 15-20 minutes, I've found out that Tom is a really cool customer who doesn't get flustered or anything. In fact, I was getting flustered and he got that, so thank you very much for that, Tom. A little bit of housekeeping tonight. I'm going to introduce Tom. Tom's going to give it to talk. Then I'm going to invite questions and answers to Tom. So I'll be asking you to shout them out. And I'll relay them to Tom, and you'll hear the answers from Tom directly. We'll thank Tom, and then we'll have a break, a cup of tea, a chat, and please, if you can pay your money for your tea, that we most appreciate. We made a loss last month, so we're trying to do this a little bit different. But we'll explain all that at the interval. Then, as we're having our tea, I'll put up the presentation for our club news, our targets for the month, and a fantastic number of astrophotographs, which is great. They all come from you guys, so it's there. And then I reckon we're going to have max of about 15 minutes. And I think what I want to do there is ask questions about something that came up from the big consultation thing we did last month. Really useful, and you'll see that in the club. However, let's get into introducing our speaker. Now, Tom's called this "You Can Almost Touch the Stars." And he's going, the stars are possibly distant, but despite these great distances, astronomers have learned an enormous amount about them. And one of the tools and techniques is a technique called spectroscopy, which is the science of analysing the colourful rainbow spectrum produced by a prism light device. One of these open slides, and perhaps is the open slide, looks like a cover of a Pink Floyd album if you're old enough to remember that. See that shortly. It says until recently, spectroscopy was too expensive for uncomplicated for the amateur to do or specialist equipment. But you can actually carry this out to hopefully you can carry this out our club. Because we bought a filter just before COVID, and we never got a chance to use it. So I'm hoping, Tom, that we'll learn enough to, get a chance to go out in the field and use it. Now, Tom was a contributing editor at the Sky and Telescope magazine from 2011 to 2021. He's the author of the RSpec software, which received the Sky and Telescope Product Award. Tom is a popular speaker who spoke to hundreds of clubs via the web. I went on and did a little survey of some YouTube, and yes, you certainly are very popular, Tom, so thank you for giving up your time and coming to speak to us. He speaks at many conferences, the Winter Star Party, and the Advanced Imaging Conference, and others. So very well regarded. So we're very lucky to have you here. And Tom, without further ado, the floor is yours.
Thank you, Eric. And I'd like to thank the two of you, both Eric and Lisa, for the work that goes into making a talk like this happen. Surprisingly large number of emails, and it's work, and especially to feed the machine and having to put together things of this sort for regular meetings. So I appreciate it, and I think you all need to also. So thanks for that introduction. I'm going to talk for about 45 minutes. It's a topic I love, and I'm happy to answer questions or my email address I'll show at the end. We've got a lot to cover, but I think that you'll be excited to hear what I have to say, because we all share one thing in common, and that is our love of the skies and the experience. Well, we love the skies, but I think we really just love the experience of enjoying the skies. And what I'm going to talk about can really deepen and enrich that experience. So I'm going to share my screen here, And let's do that. And there we go. And give me a second to move some things around. Okay. So I'm going to talk a little science, a little astronomy, a little technique, and then we'll clean up the end and talk a little bit about how you could do this yourself. You know, even if you're not an observer, you don't have a telescope, or maybe you don't do any astronomical imaging, this is still a topic that can enrich your life, because so much, as you heard Eric say, so much of the research in our field, so much of what we know comes from spectroscopy. Now, I want to apologize for my accent, and I'll slow things down a little bit because sometimes I go a little fast verbally. And let's jump in. So this is a spectrum of the sun. We have split the sunlight into a rainbow, and then we've stacked it up because it was too long. And hidden in all those dark spaces is an enormous amount of information about the sun and the stars. And we're going to look at those. I actually forgot. My wife always tells me to dress for success. And so this, I think, is appropriate, especially given, you know, I'm trying to be color coordinated and all. She assures me this is not what she means when she says dressing for success. Given that it was Halloween last night, maybe she'll cut me a break here. So, you know, just a little background, and that is everything that you know and that I know about the stars is the result of centuries of study with an enormous number of people building up knowledge, and probably even a larger number of people working hard but not contributing. You know, they went off and they showed that a particular path wasn't going to be fruitful for inquiry. And so about 12 years ago, I realized that I really wasn't all that excited about astronomical imaging. It was a little boring to me. How many images of M42 can you capture anyway? And with light pollution being a problem, I wanted to go and do some science. I wanted to learn some science. And you know, it's a challenge. You all know that as well as I do, that there are so many sources of learning. And unfortunately, there's only this one sort of slowpoke mind, weak memory, lack of motivation, time. And where do we go to learn about the stars? And how do we learn that in a way that is, you know, easy and sticks with us? So I think the foundation, and we're not going to spend a lot of time on this next slide, but the foundation of our understanding of the stars is really shown in this poster. It's called or chart. This is the HR diagram. And like I said, we're not going to spend a lot of time here. Here's all the stars on the main sequence, and the sun is here. There's Vega up here. We've got some giants, and you know, this is a temperature scale down here, you may remember. You don't need to understand this chart for what we're going to talk about tonight. But you know, the cool stars are over here, and then the hotter stars are over here. So I wanted to understand a little bit more about this chart. Like you, I had seen it. I sort of knew what I just said, main sequence, sun, you know, stars moving through their life cycles, but it wasn't mine. I hadn't assimilated it, and I didn't bring it out in my mind when I was observing. So I want to show you some quick examples. First of all, here is Pleiades. There are the four sisters right there. Keep your eyes on them. There they are here in an image, and there's a spectrum. This is a rainbow. This is done with a really inexpensive Canon. It's GTX, some sort of small Canon telescope. And aesthetically, it's very pleasing. And I want to talk just real briefly about how we can capture these kinds of images, because one of the misunderstandings I had when I looked into this is I thought, there were many, but I thought that I was going to have a lot of expensive and hard to use equipment. And I was wrong. So what I want to do first, let's go to this one slide. I want to talk about this filter. It's made in England, and let's hit escape. And actually, that's not what I wanted to do. What I wanted to do was stop sharing for a second because I wanted to show you here in the background. I've just turned on a gas tube that has helium in it. And here's that star analyzer. I'm just going to hold it up here and see that spectrum. Let me get it oriented here. See those lines there? That's the spectrum. There's the lamp. And you can see some yellow and blue and purple. So helium lamp like this one has a very specific signature. That's its spectrum. So if we put this on our telescopes, we're going to see the same kind of thing. We're going to see a spectra of the star. So let me share my screen again and go back to here. There we go. And I just wanted to real briefly show you, after I turn off this lamp, how easy it is if you do any imaging today for you to take a star analyzer grating like this. You can mount it on the lens cap threads of a DSLR. We have a small adapter that screws into those threads. Of course, any sort of astronomical fits camera. You can, if you're using your DSLR on a telescope, we have a T-ring mount for it. You can even do video, and that brings up a second point that I was confused about. When I got started, I thought that I was going to need expensive equipment and that I was going to need a color camera. You don't need color. Color is more intuitive to newcomers, but of course, like in most imaging, mono works better. And we could also put the grating in a filter wheel. So it's really easy. There's a few calculations that we help you with, or you can do on our website. It's not as exacting a science as focus, but there's some considerations in terms of mounting it that are easily understood. So I want to show another example of what our beloved Orion's belt. They're the three bright stars. And first of all, I want to come here and tell PowerPoint to leave my arrow. Now, you know, Bill Gates lives not far from here, different neighborhood for sure. I keep wanting to go over and knock on his door and say, Bill, for goodness sake, why do you make me do what I'm doing right here? In fact, I paused too long and my mouse cursor disappeared. I'm trying to tell the software, and there's no way to set it permanently. So every time you have to go out, every time you go out, you've got to come in and hit your pointer option so your mouse stays visible. So there's Orion's belt, and there's a spectrum of it. This is a typical wide field view that you would get of the stars. And you can see each of these three spectra are associated with these three bright stars. It's very pretty. And if you just put this on an eyepiece at your telescope, you see this, these are very narrow, and you see those beautiful bright colors. But like here, we can't see any information in there. It just looks like a smooth rainbow. What about the science? How do we do the science? So let's look at this field in Perseus. This is visible year-round. And here's our telerod position that we're going to zoom into. And what is this? This, my friends, is a boring star field, right? It's just stars. In fact, they get in the way when we're trying to image other things. You know, they're just in the foreground. The stars generally don't have any interest to us. And the reason I point that out is each of these stars does have a story to tell. And we can read that story in spectroscopy. And all of a sudden, all of these local stars, these bright stars that we really don't think much about, except, oh, there's a constellation, there's an asterism, you know, there's a double star. All of a sudden, each star becomes a way to learn and a way to understand more about the sky. So I want you, if you will, just keep your eyes on those three stars right there. They just happen to be stars that are in this field of view. And this is here a DSLR view. And again, you can see the spectra there. And notice that some have bright spots, some have gaps. This is the kind of thing that you can see and that we're going to talk about tonight. So these gaps and these bright spots are like fingerprints, and they help us identify the composition of the star its temperature, its movement, its pressure, its where it is on that. In fact, we'll see in a moment where it is on the HR diagram. All of that information is in these gaps if we just know how to read it. And it's so easy to read. Another misconception I had, look, I don't have a PhD or master's or BS in astronomy. And what I thought was that I needed those. I'm not going to talk any math, well, a little math tonight, but almost none. And you don't need that higher order knowledge. So let's look at this first star right here, and you can see some gaps, right? This is a little overexposed there. What do those gaps tell us? Well, we can look this up in a planetarium program, excuse me. And we see the type of star. And here in the HR diagram, it turns out that it's a very cool star. It's a supergiant. It's like Betelgeuse, that star. And the way we know that is by the gaps in the spectrum. And that's how professionals know that. So that gets pretty exciting when we can start doing the same things that professionals do. So let's look at this star here. This one has a pretty smooth spectrum. There's a gap there, but there's this bright spot. What's that all about? Well, this star is a BE star. The B star says that it's that particular type of star, and the E stands for emission line. This is a blue, it happens to be blue, B stars are, a very hot star with this disk of dust that's glowing around it. It's being lit up by the high energy coming off the star. And we can see that circumstellar, I love saying that word, it makes it sound like I know what I'm talking about. We can see that circumstellar disk in that glow. So the final star here is this one. And instead of gaps, it has these bright points of light. What's that about? Well, this is what's called a Wolf-Rayet star. It's a late-stage star. We're seeing the bare core down in the core of the star. It's shed its outer shell. And this shell here is glowing. It's the byproducts. It's the soot, as if, the byproducts of the stellar fusion. Nitrogen, oxygen, carbon, and we can see that glow in these. So that's an example of the kinds of things we can see with just a DSLR, standalone tracked DSLR. And oh yeah, that was the other thing I wanted to mention. This gets hot, by the way. I'm going to take it off. Light pollution. One reason I started this is I had so much light pollution here in Seattle on the West Coast that I was having trouble getting good images. Spectroscopy is enormously immune to light pollution. And so this is the kind of thing that you can do in your backyard or your driveway, even if there's a lot of lighting there. And speaking of locales, I was looking on Google Maps where your club is and trying to understand where you all were. And actually, I zoomed in on the building you're meeting in to try and see what kind of building it was a few days ago. And I spotted a variety of names that we've stolen from you for cities and towns here. I live near Aberdeen, and I used to live in Inverness in Colorado. So a lot of those names, I don't know if that would be called cultural appropriation or perhaps just an honorific usage. I'm going to talk a little history here very quickly. Sir Isaac Newton is said to have split light with a prism. And you can see an example of that here. And you can also split light bouncing it off a very fine lined surface or through a very fine lined surface, and that's what this is. Bunsen was a neat guy. Bunsen burnt everything he could find He was a pyromaniac, I suppose. And the light went through a prism, and then he looked at the result. And the great thing is he kept a catalog of the lines and the gaps and the bright spots of everything he burnt. And that really served us even to today. Kirchhoff was a friend of his, contemporary. We won't talk much about him, just very briefly. This area here, you can see that sometimes you get a spectrum with gaps, and sometimes you get a pretty dark area with just emission lines, points. And that has to do with the temperature of the star and so forth. But notice one thing, and that is these are at the same position. If there's one here in the green, there's one down here that's green. So, and as you saw earlier, these are fingerprints. So in hydrogen, which is so common, we've even named those gaps. And what this hydrogen beta, what should we call that color? It's sort of, you know, it's I don't know whether you call them robins there, but we have the robin bird here, and this is the color of their egg. The reason I hesitate is I spoke to a club in Brazil a few months ago, and they didn't know what robins were. My apology if you don't, but we're going to call that robin egg blue. One other scientific poster for just a moment here, and that is just an illustration that each element, here's hydrogen, here's helium, have different lines. In fact, there's that robin egg blue line, that hydrogen beta in hydrogen. Okay, so what do all of the astronomers I've spoken about so far have in common? They're old white men. And there have been so many contributors who aren't in that group that I think it's important that we appreciate them. And this, for example, Annie Jump Cannon, she and her team of, they were called the computers, were prohibited as women from accessing the Harvard telescope. So they studied these photographic plates that came off of the telescope. And they did just a stunning job classifying hundreds of thousands of spectra and coming up with a categorization scheme that helped us understand the life cycle of stars. Priyamvata Nataraja is at Yale, and she studies hyperactive black holes. Nancy Grace Roman here was the first astronomer at NASA in about 1948. Imagine the challenges at that time. And she was a big, big proponent and supporter of the Hubble Space Telescope. Elisa Quintana studies cooler type M stars and looking for exoplanets. And finally, Dr. Eisler here is at Dartmouth and also studies black holes. This was a fun slide to put together. There are so many other women and non-old white men who have contributed to this edifice of knowledge. All right, thank you for your patience with the theory and your active interest in that previous slide. Let's be done with the history and theory and equipment and talk about what you can do. Now, when I'm looking for just any magazine. I don't have one, but you'd think I would. But when I give this talk in person, sometimes I ask for somebody to just pull out a magazine, go to the back page, and show us one of the beautiful, nebula or galaxies. And these images are so pretty. One misunderstanding many of us had, including me, was that I would be able to do that myself. Then I asked them to read the fine print. And it becomes clear why I cannot create images like that, because they have 20 and 30 hours of integration time. And they are mountaintop telescopes and huge telescopes and skilled operators who are patient. I'm none of that. I have none of that. The reason I mentioned that is because what I'm about to show you and have shown you so far, with one or two notable exceptions, you could do tonight if you've ever captured an astronomical image. So what can we do? We take the grating and we put it in the light path from the star, and we get the star and the spectrum. Let's take a look. This is a series of images captured at different times by Torsten Hansen with an 8-inch Newtonian and a video camera. The predecessor in terms of capabilities, perhaps, to the ZWO cameras that are so popular today. Notice the differences between stars. The hot stars are here, type B, type A, like Vega. Down here, we have the cooler M stars. Just 2 examples on this screen. Notice how these cool type M stars have these wide bands. But we don't see those wide bands up here, do we? So this is how, again, we can see temperature differences. These cool stars have these molecular bands, the details of which I can talk about briefly, but that's something for you to read about when you have an image of a type M star, which is the most common star in our sky. Because what I found is that when it's your data, when you captured it, you have a very much more commitment to understanding and remembering. The remembering comes free because it's yours. Have you ever had trouble? This is a silly question I shouldn't ask. For those of you who have children, you've never had trouble remembering your children's names, right? Because they're yours, because you love them, because you've created them. Stars are a far distance from children in importance in so many things, but they do have that in common. One other thing I'd like to show you here, and that is this here. Notice those bright or dark gaps, but they don't exist down here on these cool stars. And also notice that up here, that's the darkest gap on a type A star like Vega. And what's the color there? That's our robin egg blue. That's our hydrogen beta line. So these cooler stars show this beta line. Excuse me, these hot stars show it, but these cool stars do not. And just a quick review. You don't need to understand a lot of astrophysics to do what we're talking tonight. But remember that the Bohr model of the atom that we learned in school has these orbitals where electrons are going around. And when an electron jumps between shells like that, it absorbs energy. That's why those gaps. Each jump from different shells between 2 different shells absorbs different energy. And that's what creates these lines. That's all the physics and chemistry you need to know. So now suppose the Space Science Institute, the Hubble people, made a huge mistake and gave me time on the Hubble Space Telescope. And I came to them. Now, do you see that little gap there? Probably not. It's really hard to see on my screen and probably the same on the overhead there. If I tried to publish a paper and said, I saw a tiny gap in the robin egg blue hydrogen beta region, that's not really science, is it? It wouldn't be published. But if I create an intensity graph, then that gap shows up as a dip. So just very briefly, this axis here is brightness, intensity. So this is high because that's very bright. The brightest part of this is sort of in the center, right? These edges are sort of dim. So these edges are very low intensity, and this peak is here because it's very bright there. The main thing to show you is that dip that sees things that our human eye has trouble discerning. Now we can do science. So how do we create that graph? So my story is here in my backyard, right outside that window, I went out with my C8 star analyzer grating, a Logitech webcam, and a lot of duct tape. That's right, Lisa, duct tape. You know it well, right? So I came in at midnight. I had some video of Vega from which this is taken. My blue jeans had grass stains on the knees because it was August and Vega was overhead. The next morning, I tried to process this image to create a graph and I failed. There was freeware out there. I downloaded it. I tried it and it crashed. And not only did it crash, but to add insult to injury, the error messages were in French. It was very frustrating. I quit. After a day or two, I went to my wife and I told her I'm through. I took the grading. I don't know why you need this visual aid, but I'm going to show you. I put it in its box and I put it in the drawer right down there on the floor because this is a hobby. I wanted to have fun, but it kept bugging me. I wanted to do science, not a PhD, but I wanted to understand more about the stars. So I figured, next weekend I would create a program to create this graph and take a few days. And now, I don't know, 10,000 hours later, I'm almost done. My wife says, please finish the software so we can have dinner at a decent hour. So the software looks like this. This is a gas tube like the one I showed you here, same one. And there's our hydrogen, there's our robin egg blue line, and there's the intensity graph. Now, I'm at least smart enough to know that if I give you a long software demo, I'm going to start, especially if the microphone is on there, I'm going to start hearing noises as people's heads hit those collapsing tables there. So I'm not going to do a long software demo, but I do want to show you very briefly, because this is not like PixInsight that's like climbing Everest, right? This is easy. There's from my first night, the star and the spectrum. There's a gap there. There's a gap in the robin egg blue. So all we do is bracket in the region that we want to study. And over here, we get that intensity graph. So this peak here is the star, right? And the spectrum, of course, shows up over here. And this deep dip here, for example, is that gap. Now we are doing science. That's literally all it takes. So what are these dips? Who cares, right? How do we do science, Tom? You keep saying science, science, science. So remember I mentioned Bunsen kept good records of what he burnt. And those records are still available to us today, as well as more accurate records. And we can say to the software, show me where on here with a template overlay, the hydrogen absorption lines should be if there's hydrogen on Vega here. And look, we have a dip there, we have one there, there. So our template matches our red data. That's pretty exciting. We're now doing science. That's all there is to it. There's a few other steps, but nothing that we can't cover during Q&A if you ask the right questions. But my software comes with a large video library of short videos where I sit and show you, like I'm sitting there with you, how to use the software. They're all on the web on our site now. You can use them there. And also I wanted to show you something pretty. That's what the spectrum looks when it's colored. So last thing on this screen, this is actually a video I made that first night. And I'm going to start it playing back. Notice my graph is jumping around a little bit. Why? Well, because my seeing is changing. So I can stack it in the software with a simple stacking algorithm and things stabilize nicely. So whether you have a video camera, and notice if it's a video camera, we're talking half-second exposure times on bright stars. You don't need these long exposures to have fun stuff to look at. Okay, that's it for the software. We're done, except to look at examples. Now, again, thanks to Bill Gates, I did have some friends who drove to his house when it was being constructed, his $50 million estate. And they parked in the back, and they were there for about 2 minutes, and a big, huge Ford Suburban van with tinted windows pulled up behind him. And it was security, so our friends left. But we can motorboat past his estate, and when you go past it, very close to it, some very big men come out with arms crossed, and they have little microphones, and they're talking to somebody, and they're just letting you know they know you're there. So he's got good security as well, perhaps, unfortunately, that he needs. So this here, I have an example. You need not see more than this. Is just for classrooms to look at these gas tubes. It's a product that we sell to educators. If the club does outreach, or if you want to start going into chemistry and physics and astronomy classes, because this is pure chemistry, and chemistry classes can't avoid this topic, because those electrons jumping is the core, is the foundation of chemical reactions. So it's a great demonstration that you can do. So we've seen this slide already now with those gaps, so we're just going to move on from that. And we've also seen this Wolf-Rayet star. Now, some of you, we saw a different one, but just I wanted to show you, Janet Simpson is in the UK somewhere. I don't recall. It was probably 10 years ago. She sent me this. And this was just with a DSLR and a mechanical tracker that she could see this glowing carbon, this soot and nitrogen and helium in the glowing shell around this aging star, probably headed to becoming a supernova. What about our beloved Ring Nebula? You can see there again, just two colors. And this is an extended object. It's really the only one that works well with our inexpensive grating, which I've now misplaced, so I'm not going to be able to wave it around in front of you. So I wanted to point out, for extended objects and more resolution, we then jump to more expensive devices like these from France. You can 3D print some for $400 or $500, but these are more difficult to use because now you're guiding and tracking and capturing data on a 20 micron slit or so. Here's the Orion Nebula, and you can see the same emission lines, hydrogen and oxygen. Of course, this is a birthplace of stars. Now, I want to pause for a second and ask you to remember the first time that you saw M42. It was probably some time ago, right? Now, for me, it was in 1991 or so. A Shoemaker-Levy 9 was coming. I wanted to do this astronomy thing. I went to a star party in downtown Denver. I got out of the car and walked up on the berm next to the observing field. It's fun when you can remember when you didn't understand something and appreciate the knowledge that you gained. Because when I looked down on that observing field, what I saw in my ignorant eyes, you know those cannons at the circus that they shoot people out of? That's what I thought I was seeing. I'm going, what are they doing with these circus cannons? Of course, they were Dobbs. I queued up. The operators were people like yourselves and myself. It was public outreach. I was all excited. They were excited. We're going to see something beautiful. I got to the eyepiece and I was really disappointed. It was a smudge. It was a mono smudge. What about all those color, beautiful images I've seen in magazines? Of course, there was urban light pollution. But here's the thing. You may have experienced that too. But I bet you, like me, still look at M42. Why? If it's a smudge. Well, we have better telescopes. We have dark sky sites. And of course, we also are much better at averted vision, right? We know how to use our eyesight better to capture photons. So, but I would say one strong reason we still look at M42 is because now we understand what we're seeing. It's a stellar nursery. It's the birthplace of stars. my point is, when you bring understanding to the visual experience, the eyepiece, that understanding enriches the experience. And that's what spectroscopy has done for me. I am a really broad river, but I'm very shallow. I can't tell you much more about the things I'm showing you, honestly. And there's no exam. Who cares? If I'm curious, then I read. If I forget it, who cares? But the excitement of understanding things with data I've captured makes all the difference. So this is Uranus and Neptune. You can see some gaps in the spectra coming up as these deep dips. And much like the cool stars, these are cool objects. And these are molecules that can survive in that atmosphere. These are methane. On a backyard telescope, this is Torsten Hansen again with an 8-inch Newtonian. Professionals 50 years ago would have given their left leg to do this. And now you can do it with simple equipment. There's the gap and there's the spectrum. So many years ago, the New York Times thought that observing the spectrum of a comet was significant. And listen, if Hank can do it today, so can we. Let's look at the spectrum of a comet. The comet is an extended object, but it has a nice compact core, this one. So we can see, even with a slitless grating, having lost that, oh, there it is. I put it in the box, giving you that nice self-conscious demonstration. There it is. So even with a star analyzer, even without a slit, we can observe this particular extended object. Beautiful string of gems here in the spectrum in my software. There are, again, the emission lines, the swan bands with just a DSLR and a small refractor. So this was captured by an engineer in India, Vikrant Agnihotri, who was a beginner when he started all this 10 years ago, and now he is really, really good. Just a quick story, and maybe this shows my cultural centricism. When he came to me and wanted to buy the software, I figured, you know, he's in India, and I've lived in India and visited many times. And so I thought, you know, he probably doesn't have a lot of money. So I gave him a discount. Well, now on Facebook, he's sharing with me his new telescope. It's a, you know, like a 14-inch huge thing. And, you know, he's got tens of thousands of dollars of equipment. So I've told him no more discounts. So here's again, another example of NEO-WISE more recently, 2020, and you can see the sodium line here. This I love. Anyone who uses a C-clamp as part of their setup, this here is a star analyzer grating on a video camera, and Robin Leadbeater, who designed the star analyzer and is an expert, captured this spectrum in mono. There's the meteor, there's the spectrum, there is a bolide, some sort of outburst. And now listen, if spectroscopy is a niche activity, then meteor spectroscopy is a niche or niche in a niche, however you pronounce it. We're not going to spend much time with the sun. We've heard a lot about it here in the US, and we have another total eclipse coming in a few years. Again, I'd love to talk more about it, but when right at the moment of during totality, the sun is small and safe enough that we can use a grating and see the flash spectrum, which is how we discovered, as you may well know, how we discovered helium. So just a quick refresher, Doppler shift. I wish, you know, 30, 40 years from now, when all of our trains are silent, this won't be an easy example. But when a train comes through a station, if this whistle on your, you know, it goes high to low pitch, right? High coming towards us, low going away, right? That's Doppler shift. Long stretched waves as if, or compressed waves. Now, same thing with light when something is moving. So suppose we were expecting this triplet right here. But instead of seeing it there, we saw it over to the side. That would mean the object is moving away. How do you think we measure all this radial velocity and the cosmological expansion, which we'll see again in a moment? It's with spectroscopy. If that triplet there was shifted to the left, it would be called blue shift towards the blue, and we'd know it was coming towards us. Let's look at how we can do some pretty cool science with that. An exploding supernova, a particular type 1A. This will be the fastest description of a type 1A you've ever heard. Two stars orbiting each other. One's bigger than the other, although that's no longer seemingly a requirement. One dumps gas onto the first one, and it explodes. Pretty simple, right? Type 1A supernova. Here in M101 is a supernova. There's what another supernova, closer to us physically, but further away in time. This is from 300 or 400, or actually 600 years ago or so. But notice it's got some shape, right? It looks sort of like a disk or a sphere. We can see through it maybe in this area. So there's the spectrum. David Strange, and he's at the Lockyer Observatory, captured with just this 9-inch SCT in less than 15 minutes of integration time, this spectrum. So that gap there becomes that dip. So let's look at some of the science that we can do, because this dip right here is how we know this is a type 1A supernova, and it's how professionals know. Now, there won't be a quiz on this next slide, except to show you that type 1A, right, these two stars circling each other, supernova, has a very deep dip above 6,000 right here, and it's silicon, ionized silicon. So that's how we can learn about stars. And in fact, when a bright object appears in the sky, by looking at its spectrum, we can learn that it's a supernova. And watch this. This is the only math that you're going to hear tonight. We note the wavelength, the color of this dip is at 6150. Now we look at, if we burn silicon, which is what this is, in the lab where it's not moving, that's the wavelength we'd see. Two different wavelengths, Doppler shift. I don't know the Doppler shift formula, but Wikipedia does. And here's our math for the night, a division and a multiplication. When we plug these numbers in with the speed of light, we get the speed that that shell is coming towards us. There should be two wows here. One is wow, that's fast. The other is wow, I can't believe I did that with an SCT in 15 minutes of integration time. This is the science that we can do. Not only can you and I do this, but Adam Rees and his team won the Nobel Prize in 2011 for using supernovas like this as standard candles to measure cosmological expansion. And now we've done that in our backyards or at a dark sky site. What about the spectrum of a black hole? We're getting near the end here. Well, of course, a black hole doesn't emit any light, but the accretion disk, as it spirals in so fast, is glowing. So here, David Hayworth captured 3C273, a quasar, black hole. I wouldn't be able to find it. Back when he captured this, I think it was star hopping that did it for him. And there's the spectrum. See those two little dots at the top of the arrows? There they are. Let's look at the spectrum. There's some big peaks there, right? Emission lines. This is a glowing disk. But what are they? This man was about 25 years old, Martin Schmidt, in about 1965 when he saw this spectrum. And he wondered, what are those peaks? So like any scientist, he compared this unknown to a known. And what was the known? The hydrogen bomber lines, like the ones we just saw from Vega in my software. There's that robin egg blue absorption feature. Except when he compared them, they didn't match, right? This line here doesn't have a peak up here, right? This peak here didn't have a bright line down here. This dip doesn't really match any dips up here. And what about all these dips? They don't even appear. So he concluded, I guess these aren't hydrogen, except they were massively red shifted from cosmological expansion. We're measuring cosmological expansion shift, the red shift, with a backyard telescope. This is by Robin Leadbeater also. This is not some image captured on a mountaintop by some pro. This is captured by hundreds, if not thousands, of amateurs with relatively modest equipment. It's pretty exciting to be able to capture data like this. And we were able to calculate fairly closely what the redshift was of this quasar. It's 2 billion light years away. What was exciting about this is that it was so far away and yet bright enough to see. It must be enormously bright. This is Martin Schmidt when he was 25. There's a great transcript on my site. I can send you a link to it if you're interested, where he describes this discovery and his fear that he was wrong. He went home that night to his wife and he said, something terrible happened today. She thought, terrible? And he was drinking wine, which she said he didn't normally do. He said, I think I made a big discovery. And he was worried that he would become a celebrity and he would not be able to work because of his celebrity status. Today, everybody pursues celebrityism, right? But he just wanted to do his science. Now, he was 25. The amazing thing about this light is it's 2 billion light years or so old, and yet it still has this data that tells us what we're looking at. Unfortunately, most things in the universe don't age that well. Here is Martin Schmidt a few years ago. He just passed away in the last year or two. Now, he has a full head of hair here. People accuse me of throwing him under the bus with these two before and after photos. I'm just jealous of the guy. What can I say? Okay, 2 more quick examples and then we'll finish up. I appreciate your hanging with me this far. I hope these examples have been interesting to you. First of all, these hydrogen features, so far, like hydrogen alpha here, how wide is that? That's about 50 angstroms wide. If we want to look at the details of that, we need a slit device. Now here, if you spend $3,000 or $4,000, which is what this costs, you can see the details of that dip. And you can compare it to other objects and measure its Doppler shift, its radial velocity. And finally, this example. I have a prop here. This is a spinning star. I guess I should be using a football for presentations to Europe. This edge is moving away from you, right? So that light is redshifted. This edge is coming towards you. So that light is blue shifted. If a star is moving very quickly, then that red shift and blue shift from the edges will spread this dip out. Vega doesn't spin quickly, but look at Altair. See how the dip isn't as deep and it's broader? That broadening, we can calculate the rotational velocity of the star. We are standing on the shoulders of giants. Who would think that we could calculate the rotational speed of a star at such a great distance? So how do you get started? Very briefly, Star Analyzer, this is in US dollars. You can buy it from the manufacturer in London for, I think, about 140 euro or so. You need a camera of some sort. You need some sort of software. This is freeware out of France. It considerably improved over the years. The authors of this I consider friends, and I've met with, and we enjoy talking shop. You may need some adapters because, as I mentioned earlier, this distance, while not critical, needs to be in a certain range, and I can help you with that. There are a ton of books. I'm worried that with all the science I've spoken about tonight, that you'll be concerned that this is hard to understand, and it's not. So my site has links to a variety of books, including the one I just showed you, that has great photos, shows you what to expect. But to be honest, I don't know I can't remember what a Seifert galaxy is. So, but he explains why these features are there in the spectrum, and can make dim-witted people sound like me, which is I'm dim-witted and I sound like I know what I'm talking about. We have a great online forum for learning. And our website has a great getting started manual, and the AVSO as well as the BAA there in the UK have a real commitment to spectroscopy. The BAA and the UK in general does the most sophisticated spectroscopy with France of any country. And I gave an hour-long workshop on how to use my software to the AVSO, and it's recorded and free on the site. You could, tomorrow morning, download my software. It's free for 30 days. And on a second monitor, set up that YouTube video of that presentation I gave them and step through the steps. Even if you never plan to do it yourself with a telescope, you would know in your gut how this all worked. AAS, again, there's opportunities to do a variety of professional spectroscopy collaborations. So we have come a long way in the last 45 or so minutes, as well as the last 200 or 300 years. The giants' shoulders upon which we are standing were giants. And for me, I wanted to understand what they did a little more, and how it is that I could do some of the things that they have done. I think you're probably tired of hearing me talk about just how exciting it is, how nourishing it is intellectually, the opportunity to do outreach in schools or at star parties. I've set my telescope, a 6-inch refractor, up with a video camera outside professional conferences. I'm always a little embarrassed because I'm an idiot and they're postdoctoral Hubble researchers. And here I'm saying, hey, look, you want to see the spectrum of Vega right now? Many of these professionals have never seen a telescope hands-on as close as I'm showing them. And they don't believe that it's possible what I'm doing. You can do that if that's your cup of tea, which I know you're headed for in a few minutes. So I want to thank you all for your time tonight, for the outreach work that you do. I think it's important for us. If you have questions now, as I said, I'm happy to answer them. I'd like to thank Eric and Lisa for setting this all up. Eric, I hope that you've been able to understand me as well with my accent, as I'm struggling to understand you with the echo in the room and your accent. Anyway, let me stop screen sharing, and then you can carry on from there. Go ahead.
Tom, can you hear me, Tom?
I can. Thank you.
That was excellent. I'm so glad you steered away from maths and all those kind of horrible things. We as a club, we try to keep astronomy, enjoyable, observation, appreciation, acknowledging its awesomeness. Some of us like to do a little bit of science, but our biggest thing we want astronomy for everyone, the ordinary person, is to be fun, and that comes over in spades. That's what you seem to want it to be as well. Interesting, we have a star analyzer. That's exactly what we've got. So I've got time for a couple of questions for Tom, if anybody's got any. I was hoping Pauline would have some, because it was Pauline that encouraged us to buy our star analyzer. We went for some software, and I can't remember what it was. I recognise the French comment you made, because when it doesn't work, yes, you get your error screens and your help screens, and they're in scientific French, which is different from conversational, colloquial French. So You won't have heard this, Tom, but you've made a sale, I think. And what Pauline was saying, we tried to use it. We got the coloured pictures, they were really quite funny. But the software was so difficult that it put us off.
Well, you know, just one quick thing, you know, and I really don't want to throw people under the bus because it's not deserving. The software that I experienced has really been revolutionary in opening this field, and the people who wrote it enormously helpful to me as well as to the community in creating this field of study. But they also acknowledge that they're not professional software developers. And that's my background. And so I brought many decades of experience, and I struggle. In fact, when somebody asks for a new feature, I worry that the feature is going to complicate the screen with a new menu or a new button. And so I anguish, you know, even if the feature is easy to implement, where am I going to put this button to keep it simple? So I'm proud of what I've done. And I think that if some of the attendees there look at some of the videos on my site, they'll see that that the software is very easy to use. And again, honestly, it is a business. I'm retired from my day job. This is my fun retirement project. But what it means is that I have time and a commitment to helping people get started. There are a lot of online forums who do the same. I think I'm a little more responsive and also oriented towards that process of helping people. But anyway, are there any questions about the science, or you can expose how little I know in the field with just one question easily, I'm sure.
Yeah, I've got one question coming. The question was, if you're taking the spectrum of say a 200 million light year away on average galaxy, how do you know you're getting the spectrum from the stars in that galaxy, not something in front of it?
Good question. That's hard to do. I alluded to that when I was talking about how the stars normally are just interfere with our normal life of imaging. And that happens here too. For galaxy spectra, they're so dim and often so enormous visually that we really do need, except for compact galaxies like that Ciphered galaxy I showed, we do need a slit. And then with the slit, it's very easy to exclude the stars that are between us and the object. But the questioner is correct that the stars can interfere with the galactic spectrum. It's a good question. I'm glad you're thinking about that.
Well, Tom, thank you very much for giving up your time.
Sure.
It looks like you're a bit warmer over there than our temperatures here, although they are quite warm. But thank you for giving up your time. We will make up a handmade card for you, and we'll post it over to you, and we'll get some details of you. It's very likely you're going to hear from one or more of us regarding your software. So we will keep in touch. But Tom, once again, thanks very much. And if the audience can show their appreciation in the usual way.
Good. Uh-oh, there's Lisa. Oh, there we go. I can see the audience. Great. Even somebody in the back wearing an orange-red jacket. Anyway, good night, everybody. Have a great evening tonight. Thank you again.
Thank you very much once again.
Good night. Lisa, I'll send you that address. Good night.